Hello team, in this video we're going to talk about Docker. So Docker is a set of tools that introduced the technologies and practices that we use today for building containers. So Docker containers are small and they run a single application. So this is one of the main ideas behind Docker containers. So Docker containers run one application and we build one container image per application. So the image is the specification of how the container runs. It's like a disk and it contains the files that are going to support that application. And because Docker containers run a single application, the images are small, which speeds up download. So when we need to run a new container, we can download its image rather fast. And starting the container is fast as well because there's a single application to start up. So this image that we see here on the right captures very well how a Docker container is built. So we have a set of libraries to support one application, and this application might talk with the rest of the world through the internet or with other containers running on the same machine or on servers in the same data center. The libraries and dependencies needed to run the application are bundled within the Docker image. So this means that a Docker container doesn't depend on anything running on the host operating system. And a Docker container can run on different operating systems. So we can have the same Docker container image run on Red Hat, CentOS, Debian, Ubuntu, SUSE. It can even run on Windows. So one image runs everywhere because the image bundles all of the dependencies of the application. This makes it very easy to ship applications and deploy them. And finally, a Docker container image is read-only. So even though the application can write to the disk inside the container, these changes don't persist if the container is restarted. So whenever the container restarts, it starts from the baseline image of that container. So any changes written to the image are lost when the container is restarted. And this makes it easy to reproduce the execution of a container. So every time the container runs, because it runs from the same initial state which is configured in the image, the container will run exactly the same every time. So Docker has a lot of tools around development and deployment of containers. So to build containers, we write a Docker file specification, which is similar to a make file. And then Docker will read the Docker file and build a container image. We're going to see an example next. And Docker has other tools that we use, for example, to start containers and configure containers, modify containers, inspect containers, get a shell inside the container. So it has a lot of tools that we can use to manage the containers. And Docker also has a large image registry called Docker Hub, where anyone can upload container images. And this means that we have many ready-to-use containers and applications. So some applications that are a little bit tricky to install are sometimes available as Docker images. So if you want to try an application out, it's very easy to download the Docker container and just run it. And also, this large image registry helps us build more complex containers because we can use the existing images as baseline for a more complex image. So here we have an example Docker file. So here, the first line is this from line, which specifies what's the baseline image that we are going to use. And the baseline image we are going to use is this Python 3.7. It's an image of a Linux distribution with the Python interpreter installed already. And we're going to use Python because Django uses Python. So we need Python in our container. And we also use Debian because that's what we use in all of our servers. So this is Python, and we're going to use version 3.7 of Python installed on Debian Buster. Now that we've chosen our baseline image, we're going to modify this baseline image so that we can run our application. So this is a Django application. So we're going to install Bird, which is one dependency, and then libgit to interact with Git, which our website does, and then procps so that we have some minimal tools to operate the container once it's running. So install these packages, and then we install our application inside the container. So all these run commands, they are run while we are building the image. So the container isn't running yet. We're just preparing the image. So we started from Debian with Python, installed some dependencies. Now we're going to install our application. So we're going to copy some files inside the image, and then we're going to run pip install to install the dependencies of our application. And these are, we have many dependencies when one of them is Django. And finally, we have the entry point of our application, which is what will run when this container starts. So we basically have this entry point.sh, which is going to call Django. And once Docker finishes building our image, we're going to have this file on disk that we can use to start our container. And then we can upload this file to Docker Hub, or we can send it to a different server to run the container there. Okay, so now that we have a container image, to run it, we're going to issue commands to the container runtime. So the container runtime controls the containers running on a computer. So in Docker, the container runtime is currently called containerd. So this is an open source project, and it manages the containers on a machine. So what does the container runtime do? Well, the container runtime, it configures the glue between the container and the host operating system. For example, if the container application uses the network, then the container runtime's containerd module will configure the network namespace inside the container so that it can communicate with the rest of the internet through the host OS's network. And the container runtime also configures volumes inside the container. For example, if you want to bring some data from the host OS inside the container. To interact with the container runtime with containerd, then we will use a client application, which might be a command line application or some application that communicates with the runtime through a network API. So it's very common to use the command line interface from Docker to interact with containerd. So we can do Docker run and it will run a container. We can do Docker kill and it will stop a container. So we use Docker to control the container runtime, and then the container runtime will take care of managing the containers for us. One word regarding open source and standard. So Docker is a tool set. So it started out as a technology, but parts of it have been standardized and open source. In particular, the container runtime has been open sourced and is now standard. So it's called containerd.io, but it's now open source and many companies contribute to it. And there are other controllers to communicate with the container runtime. For example, Kubernetes can manage Docker containers. Red Hat has Podman, which can also manage Docker containers. So here I'm showing Docker controlling containerd, but we could have Podman or Kubernetes controlling containerd directly. And finally, Docker containers are not the only type of containers you can run on Linux. They're very common because of their practical approach where we package one application inside each container. So this abstraction is nice and it's become standard in the industry. But there are other ways of building containers. In particular, Linux containers is a different way that relies on the same technologies that Docker uses, namely Linux namespaces. So LXC is an approach you can use, but it's a little bit different from Docker. So LXC is more similar to a virtual machine. So we have larger images, and each LXC image usually has a complete user environment. So it has a set of libraries and a set of applications that run all the time, like we have in a virtual machine. And you usually have multiple applications, like you might have a scheduling application that might be some SSH daemons running and email servers running. So we might have multiple services on an LXC container. And usually LXC containers have persistent disk images. So when we restart the container, the modifications we brought to disk will still be there. So it's not guaranteed that the container will start from the same state every time. It might just keep modifying the disk and it might behave differently every time, depending, for example, if we are modifying the configuration of the container. So to compare, in Docker, while we might build one container to run Django, in LXC, we can have a container that runs Django, that can send periodic emails to see that everything is alright, that can auto-update itself, for example, using apt-get upgrade, and it can, for example, renew certificates when they're about to expire. So an LXC container can run multiple applications at the same time, and this is the more common approach to building them.